Section 2 of Chapter 4 is all about finding the area underneath a curve using what we call a Riemann sum. And it can seem like a very, very different type of thing. It's very different from everything we've been doing in this class so far, but it's very relevant to what an antiderivative does and in towards leading to understanding the fundamental theorem of calculus, integrals, and other things like that. But it's helpful to think about the previous video where I talked about the relationship between acceleration, velocity, and position and how derivatives and antiderivatives do such a thing. But basically, let's look at this particular example, which is talking about, let's say we're traveling at a particular rate of speed. And let's look at how the area underneath the curve describes the accumulation of how far we traveled in that period of time. Because not to get ahead of ourselves, but what an antiderivative does, so geometrically, is that if we want to use an integral symbol can be used to figure out area underneath a curve. And it can be used to solve a whole lot of other things too, but the logic of this is not obvious unless you spend a lot of time thinking about it. But let's look at this example. Let's say that we are moving at 15, it says in miles per hour. So this graph represents 15 miles per hour. So imagine you're like riding a motorized bicycle. I guess, I don't know if those go 15 miles an hour, but just pretend they do if they don't. And you want to know, well, how far did I travel as I was riding my bike? Well, if you travel 15 miles per hour for 1 hour, of course, that means we've gone 15 miles because I spent 1 hour at a constant rate of speed. And now actually, if you look at what a graph of a velocity function does, well, this would be just a horizontal line because basically what this is saying is I'm going a constant 15 miles per hour. But if I look at the area underneath the curve of the velocity function, it will actually tell me how far I traveled. And notice that in 1 hour, the accumulation of that is, well, of course, the width is 1. If I, again, based on basic rectangle math, right? Area is equal to length times width. The width is 1. The height, or length times height, whatever you want to call it, width times height. The height is 15 because that's a constant. Well, 1 times 15 would give me 15. So the area there is 15. So basically, I have gone 15 miles in 1 hour. And that is not a coincidence, that the area represents the total time traveled based on the speed. And if I extend that further, right, if I'm going another 15 miles per hour in another hour, well, I would have traveled another 15 miles in that period of time. And so there's a connection between how fast I'm traveling and how far I traveled based on the area underneath the curve. And the area represents exactly that, the accumulation of velocity. It's like as my tires are going, they're accumulating distance traveled. And that is measured by the area underneath the curve. And if you're wondering, well, why? There's not necessarily a good explanation to why. It's just sort of how it works. Just like how derivatives give us the slope at a particular point in time, which measure, well, the exact opposite phenomenon. How fast am I going? The instantaneous velocity at a particular point in time. Now, looking at another example over here, we have a graph where the velocity, let's again imagine we have a bicycle and then the purple or red line or whatever represents our speed. Let's say we're starting from rest and then we're speeding up. We're accelerating on our bicycle, meaning like after, it looks like after 2 seconds, we're going approximately 6 feet per second. And then after 4 seconds, we're going, it looks like maybe 12, 13 feet per second. But basically, every second we're going faster and faster and faster, which is what this means. Essentially, the area under the curve represents how far we traveled in that increment. Like if I'm going much slower, I have not been traveling as far. So like this area would represent the distance I've traveled within the first second. And then over here, I've traveled a lot further because I'm going faster. And as I go faster and faster and faster, like you can kind of imagine sketching out a diagram of this. Well, like we start in the first second going slowly and we're accelerating and then accelerating and accelerating. And as I'm accelerating, I'm going farther and farther and farther because I'm getting faster. So you can't see that, me trace that, can you? It's not working. But it's like after 1 second, I'm going very slowly. Then in the second second, I'm speeding up. So I've gone farther. Then speeding up farther, and so forth. It's kind of like, well, how far I traveled in each increment is dependent on my speed. And, a graph like a line, velocity function where my speed is increasing and increasing, would mean that in each increment, I have gone farther and farther. And it's kind of like, well, each of these is the respective areas under the curve. Like in the first second, I went this far. And the second I went this far. But essentially, it's kind of like I can use the area under the curve to visualize the amount of the distance that I've accumulated in that period of time, as I was describing up here. So all this idea leads us to what we call Riemann summation. The point of this is trying to figure out how much area is underneath the curve. Like with a straight line or with a triangle, it's very easy to figure out these areas of these particular regions because they're either rectangles or triangles, and the formulas for those are very simple. But if you can imagine, let's say we're dealing with it's more common, say as you're riding your bike, you're speeding up and you're slowing down. Again, imagine this is the velocity function, which represents at a certain point in time, you're going downhill and you speed up. And then you reach the bottom of the hill, and then you start having to climb uphill. Naturally, as we move around the earth on a bike or on a car or whatever, our velocity is not typically constant, or it doesn't necessarily follow a nice straight line. There's changes, there's ups and downs, there's mins and maxes. But all of that being said, the question is, what if I wanted to figure out, like, let's say that this velocity graph represented like my bike ride for the morning from 0 minutes to 30 minutes. And this is kind of like the speed that I traversed over that whole bike ride. But the question is, I want to know how far did I travel? Well, of course, you could have an odometer or something which measures this. And actually, those devices work by using a lot of the fundamental ideas of calculus. But rather, not worrying too much about how those devices work for right now. What about, obviously, we're trying to focus on the math. But the key here is, if I wanted to solve how far I traveled, the question I would need to answer is how much area is under the curve. That's kind of the thing I wanted to mention. And that's why area is relevant. So before we talk about how to do it with calculus, let's talk about a Riemann sum. Because the idea of understanding an integral is based around Riemann summation. And in class, we'll talk a little bit more about this, and we'll talk more about integration. But basically, as it turns out, it is very easy to solve this if I know the function. All I need to do is take an antiderivative of it, and that would give me the position function. Like, as I said in the last video, the antiderivative of velocity gives me position. And if I want to figure out this area or how far I traveled, this is what an antiderivative does. And technically, it's what's called a definite integral instead of indefinite. And we will, again, we're going to talk about that. But essentially, for right now, let's not worry about integrals and calculus at all. Let's just focus on finding it. And that's what a Riemann sum is. Essentially, the process of doing this is by taking a particular curve and breaking it into pieces. Like if you're looking at this graph, notice it's broken into 4 columns. But the number of columns is somewhat arbitrary. Like you could do it in 4, 6, 8, or whatever. It's sort of like, imagine slicing this into pieces. Like let's just say I slice this into 5 equal pieces. And equal is important. They have to be sliced into equal pieces. Sort of like, here's a bar graph. I could kind of think about, well, what's the area of each part separately to simplify the process of identifying how much area is underneath this particular curve that I care about, where the width of it is called delta x. And again, it's just like in derivatives, right? Delta x is sometimes like, it's like how wide is that interval over a particular point in time. But what we're assuming is that is a consistent delta x for each of the little columns of our interval that we care about. And then notice that, well, the only thing that changes here is delta x is a constant for each of these, is what is the height of each point. Like notice on this particular graph, each of the bar graphs are called left connected bar graphs, meaning that they have been, or sometimes they're called the left Riemann sum, because they've been attached to the curve at the left endpoint. Now you could also use what's called a right Riemann sum, which would be, notice here, like again, I'm kind of imagining this is the function to which I'm trying to find the area underneath the curve. It is kind of all about, where do those bars intersect with your graph? Like I have 5 bars here. And here, those 5 bars were intersecting on the left endpoint. So like if I was to do the left endpoint here, I would connect it there, 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 and there, because I would just take the intersection of the left side of the bar and move it to the right, if that makes sense. But if I wanted to do a right-handed Riemann sum or a right Riemann sum, or again, whatever you want to call it, it would be taking the right point from each. So I would take that point, that point, that point, that point, and that point, and these would make up the bars of area. And so essentially, if you do a right-sided or a left-sided Riemann sum, or you can also do a middle central Riemann sum, which it would be basically taking the midpoint. So like that is actually usually the best option, but it's more complicated. Which mean, well, on this, in between these points, there is a point right directly in the middle to which I could use that. But essentially, we're trying to figure out the area under the curve, and we can use rectangles to approximate the area under the curve. Like here, notice that the exact area under this curve would not be exactly what these bars represent, but it's a rough approximation. Because let me try to summarize this once again. Hopefully, I'm not getting too complicated here. I'm trying to figure out what is the area underneath the curve exactly. Like imagine as a slice of cake or whatever. How much is in that exactly? But that's difficult because it's curved. How do we know what that would be? And that's what we're trying to work on and understand conceptually. Turns out you can use an integral to solve that very simply. But basically you could use like a Riemann sum. The idea is you can use an approximation. You can use a left endpoint. Let's just do a right endpoint, and essentially again that would connect each of the bar graphs to the right hand side. And basically I would just make a horizontal histogram or horizontal bar graph from each of those points. And what I then try to figure out is what's the area underneath the curve in each of those points. I would then add up each of those rectangles, and the sum of all of that would give me an approximated area under the curve. It's sort of like in orange or yellow over here. I guess it's a little more yellow. That's not exactly the area under the curve that I'm trying to find, but it's kind of close. There's like, it's missing a little bit of area here. It's missing a little bit here and has a little bit too much here and here. And notice that as I'm shading this diagram into the right, it's not exactly the same as the curve, the area that I shaded a minute ago, which is what I'm trying to approximate. But it gives me a decent estimate for the area under the curve, and it helps us see the idea of what an integral means. So Riemann sums, they're not usually important for you to actually need to do, but they're important to understand what an antiderivative is. So now writing this a little bit more algebraically, it says a Riemann sum is written as f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x, and so on. But essentially, because each of these areas, they're based on the height of the function, right? Because I'm trying to find the area underneath this particular curve, which is a function, whether it be a velocity function or just generic f of x. Now, each of the height values of those rectangles is determined by the function, whether it be the left endpoint or the right endpoint. Again, it doesn't really matter at the end of the day. It will give you slightly different answers. But when we do it on an infinitesimal level, it doesn't actually matter. We'll talk about that later. But basically, noting that delta x is always the width, and the height is just determined by this point. So it's like, well, the area of each segment, we call this A1, A2, A3, and A4, is always just length times width, or height times width, whatever you prefer. And that's exactly what this is saying. If we multiply f of x1 times delta x, that would be the area of this first region, A1. A2 would be the product of those two, width times height, width times height, width times height. So the structure of a Riemann sum is a product of width times height. And it's coded into a mathematical function. That is what f of x is, right? So f of x determines the height value at each point, and delta x is a constant. It's the same for all of them, and that makes the Riemann sum easier. Because based on algebra, I could then factor out delta x, and what it would leave me with is just f of x1 plus f of x2 plus f of x3. And essentially, all I would need to do is choose delta x, figure out the location, and then plug it into the function, multiply all that all out. And this would give me an approximation to the area under the curve. And that is the key idea. Or we often write it using summation notation, using, remember, sigma, which means adding things up from index 1 to 4. But basically, notice exactly what this means. If I factor out delta x, usually we write it at the end, and then adding up the sum of the height values of those functions, those 4 points in time. Remember that how to read a Riemann sum is that you plug in 1 into there, and you plug in everything in between up till 4. So again, how this would expand, this is identical to above, because this would mean fx1 times delta x plus fx2 times delta x, and so forth. I'm assuming you guys have seen Riemann sums in your previous math classes, but if you don't really remember what this means in terms of sequences and series, I would review kind of the idea of what a Riemann sum. Just Google it in YouTube and how to evaluate. But like, let's just do a very, very simple example of a Riemann sum. Let's say we had delta, or this sigma of, let's just say x dx, x squared or something, from x equal 1 to 4. Oops, I did not mean dx. We don't need dx, or we don't even need delta x, but just how a sigma notation works, it just means that it's a shorthanded representation for adding up a lot of stuff. So instead of having to add up 4, this is the formula which represents the area of those 4 pieces. If I wanted to kind of join that into a single entity to describe that, this is how I write out repeated summation. And the index, or the dummy index I in this case, is another new variable which doesn't have any meaning. It's just used to represent, again, I for index, what points, where am I starting and where I'm ending. But it's just saying, well, I want to start at the first point and end at the 4th point, and I want to add up everything in between. That's essentially what this notation means. So like a sigma notation over here would mean, well, I want to add up everything. This is my formula. This is what I want to add up, and I want to do it from here to here. And again, it always specifies, well, what variable are we using? So all this would mean is 1 squared plus 2 squared plus 3 squared plus 4 squared. Basically, I plug in 1, plug in 2, plug in 3, plug in 4. Add it all up. But anyways, enough about the notation. I'm assuming you guys have seen sigma notation, but usually this is kind of complicated to try to understand because there's a lot going on. But to summarize, this represents the sum of all of the pieces of area of this curve. So again, this is like an the whole point of doing this is the approximation for the area under the curve based on using 4 intervals at this point in time. And another idea about Riemann summation is that the more another thing you might have been wondering is, why did we use 4 subintervals here? What was the reason behind that? Well, it's kind of arbitrary. You can kind of use however many you want. Usually how the homework will work is it will tell you, okay, use 5 subintervals, use 10 subintervals, and essentially that tells you exactly what this will be. And there's actually, I wanted to mention, there is a formula to figure out what delta x is based on your subintervals, but we'll do a practice problem here in a minute. But basically, one of the ideas that I wanted to cover before we did an example of finding a Riemann sum is, for some reason, this picture is quite blurry. I think it's good enough. So I'm not really sure why the resolution's not coming out very well. But the point was, if you use more subintervals, you get a better and better approximation for the area. Let's say that I took that same exact graph, and instead of breaking into 4 individual bars like over here, let's say I broke it into 8 subintervals instead, did it more often. We'll notice that if I did that, again, notice it's using a left endpoint to connect them together. So that's how you know how tall they are. But basically, I just get more bars. It's not exactly the same area, but it's very similar. And actually, notice it's quite a bit more accurate than the previous graph, because on the previous graph, we used only 4 subintervals, so our graph ended up looking like this instead. And those portions of area were a little bit actually worse if you really look at it, because here this bar was missing, this bar had a little extra, this bar had a little extra, and this bar was missing. And so actually this is a better approximation to the actual area underneath the curve, because notice there's a smaller margin of error. Here we're only missing, there's like, again, the point of all this is to get what is the precise area, what is all of the area under the curve in this interval, to calculate exactly how much we've got in there. And we use Riemann sums to approximate it, essentially. This one is only off by a little bit, right? This is a little too much, is off. It's a little too short. It's not quite the correct area. But again, the point is we can use rectangles to approximate. Also, we're a little bit short over here, so we can kind of imagine there's a few points where we're missing a little bit. So if I'm kind of imagining the area under the exact curve, I'm a little bit short in those particular spots. But also here we have a little bit above. And typically what it will work as a curve goes up and down is you'll have a little bit too little and a little too much. And those will kind of counteract each other a little bit. Like if you can imagine cutting these ones off the top, you can kind of paste that one in there, paste that one in there, paste this one in there, and paste that one in there. And that will give you actually a pretty close approximation, and it will be very close to the actual area under the curve. So Riemann sum never gives us the precise area under a curve, but it does a pretty good job because we're a little bit off. We're a little under and we're a little over, but they sort of counteract each other to give us a good approximation. And also, the last point is that the more subintervals you use, the better the Riemann sum. Let's say I use 24. Notice that here, the area under the curve is almost exactly perfect. There's only very, very slight overages here and very, very slightly under. But essentially, using 24 subintervals, the math behind this would take forever because you'd actually have to do 24 sums. Like, again, imagining here I have this area plus this area plus this area plus this plus this plus this plus this. You have to add them all up. So the more subintervals means the more sums you got to add. But at the end of the day, the more you do it, the better it becomes. And the whole idea is, well, what if I could do this infinitesimally small? What if I could imagine a curve and actually find the exact area? Like imagine taking pieces of string and lining them up, figuring out exactly how much area is under each little part. But that's exactly what an integral does. This is basically infinitely adding, infinitely summarizing the area underneath the curve, symbologically, or we'll talk more about the definition and so forth later. But this is the idea of a Riemann sum as n approaches infinity. If the goal is, if we could do it more and more and more, we get a better and better approximation under a curve. But understanding Riemann sums is cool because it allows us to visualize area under a curve and how to approximate. And then we can apply this to solve it using calculus. That is in 4.3. This video is getting a little long. So in the next video, let's look at the first example. Let's actually practice calculating Riemann sums. And then next week in class, we'll talk about how to take this to the next level.